Today we'll go into the governing equations for acoustics, then we'll detail the finite element formulation for the wave equation, look at which boundary conditions we typically have in acoustic simulations, and then look how the discretized system looks like, and I'll give a few tips on how to model acoustics. So let's get started with the wave theory of sound. There are a few assumptions behind that in the physical domain. So we assume an inviscid fluid. That's the basic assumption in acoustics. And that means that the fluid particles only move forward and backward. And the driving force for these acoustic waves is the pressure change in the medium. And also due to the inviscid assumption, we have just longitudinal waves that can propagate. So there are no shear waves in the domain, for example. We have in acoustic waves, or in waves in general, a periodicity in space and time. So if we look at the position in time, and we look at the field solution over the space coordinate x, we see the wave solution with the wavelength lambda, and if we look at a distinct point in space and we monitor it over time, we again have a wave-like solution or harmonic solution with the period being the time, and there is this common relation between wavelength lambda, speed of sound c, and frequency f that determines the wavelength for acoustic waves that are non-dispersive. So what are typical quantities for the wavelength, which is the central parameter in acoustics? For air, we have wave speed for about 340 meters per second. In water, we have about 3 times this, so 1,400 meters per second. And also the densities are fundamentally different into these two important media. Air has a density of about 1 and water of about 1,000, so 3 orders of magnitude larger. And when we now recall the relation of wavelength and frequency, we can see that we have this 1 over frequency behavior in the wavelength. It's the same for water and air, but of course the absolute values are different. So for higher frequencies, the waves get shorter. For smaller frequencies, we have longer waves. So here there are typical lengths. So in air, which is the typical acoustic medium at 100 Hertz, we have about 3 meters wavelength. And at a kilohertz, we only have 30 centimeters wavelength. This will be later important when we actually want to resolve the wave, since our mesh has to resolve the wavelength. But let's first look at the perception of sound. So when we hear something with our ears, we actually sense pressure amplitude changes. And the human ear is actually very sensitive. We can hear pressure amplitude changes of about only 20 micropascal. So that's the threshold of hearing. And the order of magnitude we can hear is very large. So the threshold of pain is only at about 200 Pascal pressure changes. So there are several orders of magnitude in between. Let's see how we perceive loudness changes. So the amplitude is called the loudness, and they're actually perceived equal if the factor is equal. So if we have a pressure change of P0 and we have the double pressure change, that's perceived equal as we increase from 5 P0 to 10 P0. And due to this large range of values we can perceive, we use a logarithmic scale. This is given in decibel. You can here see the sound pressure level, LP, how it is computed from the pressure amplitude. Usually you take the RMS value here, and the reference pressure amplitude, which is our 20 micropascal. And there are a few typical sound pressure values given here. So human voice at 5 meters distance is about 60 decibel. A car at 20 meters distance is 80 decibel. A motorbike close by 5 meters distance is 110 decibel. And the jet noise at 3 meter difference is 140 decibel. We can also perceive sound in terms of frequency. This is called the pitch. So here we have a sensible frequency range for the human ear between 16 hertz and 16 kilohertz. And the sensibility actually differs with respect to the frequency. This is why the dBA scale, for example, is introduced. How do we now perceive differences in pitch? They are perceived equal when the frequency ratio is equal. So if we have a tone at, let's say, 220 kilohertz, which is the A3 in music, the difference to A4, which is at 440 hertz, so the ratio is 1/2. So this is perceived equal as a change from C0 to C1, which is from 16 hertz to 32 hertz, roughly. And what is also important when you speak about pitch is the definition of an octave. And this is defined as the pitch interval with the frequency range of 2 between the higher and the lower pitch. And this enables us now to compute the middle frequency. So which frequency is perceived as in the middle of frequency 1 and frequency 2, or the lower and the upper frequency. And if you take the perception into account, this amounts to being the square root of the product. And you can do the same if you split the frequency interval in 3 parts that are perceived equal. So if we want to split an octave in a 1/3 octave filter, we have to split the frequency interval into 3 equally perceived frequency differences. Here are the relations, how you can compute the frequency spacing, and you can design so-called octave filters by computing these frequency differences. So here is the filter for a full octave, for example, the first octave from 220 to 440 hertz, and again a double, a factor of 2, 440 to 880, and then another factor of 2 for the third octave. So what are now the governing equations for acoustics? So we start by describing the fluid motion by its state variables. So we have density rho, the pressure P, and the velocity V. And these quantities must satisfy the conservation of mass, so equation 41. And the conservation of momentum is equation 42. And we usually also need a state equation, which in acoustics will be the pressure density relation to close the equation of system. And of course, we also need to, in the general case, describe the viscosity tensor tau by a material law. However, in acoustics, we said we're inviscid, so our viscosity tensor is simply described by being 0. And the second important assumption in acoustics is we only consider small perturbations from the base flow. So in order to derive our acoustic equations, we'll take the general equations and linearize them using a perturbation ansatz. let's look how this works. We want to linearize our equations. The first step is we split the base flow, the field quantities, density, pressure, and velocity in the base flow, denoted by the index 0, and acoustic perturbation quantities, denoted by the index A. So we make rho the sum of base flow, rho 0, plus acoustic perturbation, rho A, and we do the same for pressure and velocity. To simplify the matter a little bit more, we also assume zero base flow, so zero base flow velocity. So this means we have no background flow. Note this is only done for the sake of simplicity. You could also do the same with considering a base flow in the background. And then we insert our ansatz in the continuity and momentum equations, giving us these two equations. And now we can simplify them a little bit. We can consider the space and time independence. So we can see that the time derivative of rho 0, which is time independent, is 0. So this term will drop. And similarly, the rho 0 here is spatially independent. We can pull it out of the differential operator. And the P0 is also spatially independent. So the gradient of it will be 0. And then we have also some higher order terms now in red. And these will be neglected since we are linearizing around the base flow state, and we can drop higher order terms. So this yields the following equation. We have the time derivative of rho, the acoustic rho. We have the divergence of V, and we have our continuity of our balance of momentum, rho 0 times time derivative of V plus the gradient of P. So you see we still have two equations. However, we have three unknowns: density, velocity, and pressure. So we need our equation of state to relate pressure and density, our state variables. So that's the next step. We insert our pressure density relation, which can be given as the acoustic density variation is equal to the pressure variation over the speed of sound squared. We'll see just in a minute how to derive this relation. So if we do this, we can obtain the linearized continuity and momentum equations now in two variables, pressure and velocity. And finally, we can combine these two equations by taking the time derivative of the continuity equation. So here, equation 43, we take a time derivative. And for the momentum equation, we can take the divergence. And what you will see is that the velocity term can actually be eliminated from these two equations. And this yields the acoustic wave equation, where we have the second time derivative of the pressure minus c squared times the Laplacian of the pressure. So this is the equation we will have to solve for acoustics. Now let's look a little bit into detail into the pressure density relation. We can express the pressure as a function of the state variables. So the other two state variables we have chosen here is the entropy S and the density. So if we have the equation of state, we can write its total derivative. Total differential dp equals dp over d rho at constant entropy times dp plus dp over ds at constant pressure ds. And then we know that the speed of sound is actually defined as the square root of dp over d rho at constant entropy. So this is the adiabatic speed of sound, which is the central assumption we use In acoustics, we assume the changes in pressure are adiabatic, since there is no time for other energy exchange in this fluid medium. So, for example, heat conduction in the medium is neglected. So if we take this assumption of adiabatic and reversible process, we can say ds is 0, and we obtain our pressure density relation via the speed of sound squared. So how do we define the speed of sound in an ideal gas? We can use the ideal gas law to get the relation we need, and we can compute it via the square root of reference pressure over reference density times the specific heat ratio, also called adiabatic exponent. Of course, you can also express this via the gas constant R, and here you see that the speed of sound depends on the state variables, so on the pressure, the density, and the temperature of the medium. In liquids, usually one expresses the speed of sound as the square root of compression modulus or bulk modulus over the density. Please note that K is the adiabatic bulk modulus. So we have seen the acoustic formulation, the pressure formulation. In acoustics, we also have a second formulation we can use to derive the acoustic wave equation. And this is what we do now. This formulation is called the potential formulation. We'll quickly see why. So if we take the curl of the linearized momentum equation, written down here, curl of the momentum equation, we pull in the curl, we obtain a term which is the curl of a gradient, which is always 0. And then we see also that we have here an expression, curl of velocity is 0. This means that the acoustic particle velocity is irrotational. And that also means we can write the velocity field in terms of an acoustic scalar potential psi A introduced here. So velocity is the gradient of the potential field. The minus is used due to convention. The next step to derive the potential formulation is to introduce the potential again into the momentum equation. So we simply insert it for the velocity, and then we can actually relate the potential and the gradient of the pressure. In fact, we see we have a gradient here. We can also we can relate the pressure with the time derivative of the potential times the density. And finally, we can use the potential in the continuity equation, again, insert it and write the pressure in terms of the potential, and again combine these two equations. And what we obtain is surprisingly, again, a wave equation. So mathematically, these two formulations are completely equivalent. So we have a wave equation for the scalar potential, or we have a wave equation for the pressure. So these are our two acoustic formulations, the pressure formulation and the potential formulation. Now our task is to obtain the finite element formulation. So we want to write down the weak form. And as usual, we introduce a test function, multiply it with the PDE, and integrate over the domain. The test function can be constant over time. We can apply the divergence theorem as a second step, and finally incorporate our boundary conditions. So let's do this. Just as a note, for the sake of brevity, I've omitted the index A now, since we're only working now with acoustic perturbed quantity. So PA means P from now on. So we introduce a test function P prime, multiply and integrate over the domain. So this was the easy step. We have the wave equation integrated. And now we use the integration by parts. So we apply the product rule and use the divergence theorem to obtain first here a shift of the differential operator. The gradient also applies to the test function here, and the boundary term P prime times gradient P in N. And for this boundary term, we now have to insert boundary conditions. So this is the next step. We incorporate Neumann boundary conditions. We say this is a known term, the inhomogeneous Neumann term, and we obtain the weak form for the pressure formulation. Of course, the weak form for the potential formulation is equivalent, with the difference now that the boundary term means physically something else, and also, of course, the unknown quantity physically means something else, but mathematically these formulations are equivalent. Let's look what boundary conditions we have in acoustics. As usual, we have the Neumann boundary condition in the pressure formulation. This is gradient P in N. It's a normal, the so-called normal pressure, if you want to call it like this. But physically, this can be related, the pressure can be related to the velocity, as we've seen beforehand, times the density. So the time derivative of the velocity is related to the pressure gradient, and therefore we can interpret this time derivative of the velocity as a normal acceleration of the boundary. In the case of the potential formulation, this is more easy, since we know that the gradient of the acoustic potential is actually the velocity, and in N means the normal velocity. So in the case of the potential formulation, the inhomogeneous Neumann boundary condition prescribes a normal velocity of the boundary, whereas in the pressure formulation, it describes a normal acceleration. The homogeneous case means is the natural boundary condition as usual, and zero acceleration or zero velocity actually means this is a sound hard high impedance wall that is not moving. And the inhomogeneous case means we have a moving boundary, so to say, with either prescribed acceleration or velocity. So this will be an excitation boundary condition that actually generates waves that are propagating into our domain. And then we also have the Dirichlet boundary condition. So we directly prescribe the pressure or the acoustic potential. Again, we have two cases. The homogeneous case is the low impedance case. So this is a sound soft wall where we prescribe zero pressure in the potential formula, in the pressure formulation. So this would be a very large reservoir where acoustic pressures are not changing. In the inhomogeneous case, we have prescribed pressures. So this again is an excitation boundary conditions. All these boundary conditions lead to reflections of the waves at the boundary. For example, for the homogeneous Neumann case, we have a rigid wall that is not moving. Of course, we have reflections there. So often in acoustics, we have open domain problems. So we actually want to model our domain of interest here in green, radiating waves somewhere outside, and we have to truncate this domain somewhere at some time. We cannot mesh infinite space. The problem is that at these boundaries where we truncate our domain, the Neumann and Dirichlet conditions will lead to total reflections of the waves. So that means we have to assume absorbing boundary conditions in order to model this phenomenon. So to truncate the computational domain without generating reflections at the boundaries, we can distinguish two important approaches. The first is the so-called absorbing boundary condition, which I will introduce in the following. And there's also a little bit better solution, which is called the perfectly matched layer, which is basically a region around the domain of interest where the waves are absorbed in a perfectly matched manner, meaning it doesn't matter where the waves come from and they will be absorbed as good as possible. The perfectly matched layer will be covered in the next course. Let's look into the absorbing boundary conditions first. When we have a plane wave traveling in direction n, it can be described by the following relation, p hat, so this is our amplitude, times the exponential of I to the power of I, which is the imaginary unit, and then the typical wave solution, omega t minus k in x, where k is our wave vector. So wave vector has the length of the wave number omega over c, where omega is our angular frequency of the wave, and n is the propagation direction. So this n is not chosen arbitrary. Actually, this should be the normal vector of the boundary. In this sense, we will be using this condition later. And if we now look at this wave solution of the plane wave, we can verify that the relation gradient of the pressure in n is equal to minus 1 over c times the time derivative of the pressure holds. So you can do this with this solution, take the gradient in n and take the time derivative, and you will see that this relation actually holds for a plane wave solution. If we now have a first order absorbing boundary condition at our boundary gamma A, we now want to actually say, okay, our solution assumes this plane wave solution at the boundary. So this means waves can only propagate outwards and not inwards. So what we do is we replace the unknown boundary flux, so the gradient p in n term that we always have in our boundary term, by the solution, by the relation taken from the plane wave solution, which is 1 over c times the time derivative of p. And if we simply insert this in our weak form, we obtain another bilinear form at the boundary. So this is a boundary integral, not a volume integral. And here we have the relation of test function p prime times the time derivative of our unknown function, and inside also the speed of sound. Just note that the first order absorbing boundary condition can only absorb waves impinging orthogonally onto the boundary. So if we have oblique incidence angles, this will not work as well, since only the normal component can be absorbed due to the assumption we have taken in the absorbing boundary condition, which is plane wave traveling in normal direction n of the boundary. So here we have seen already how the discretized system looks like. We can take standard nodal finite elements again in the formulation, and we have a mass matrix, a damping matrix, and a stiffness matrix. Note that depending on the formulation, the vector of degrees of freedom x either contains the pressures or the acoustic potentials. The mass matrix looks as usual mass matrix with the ansatz functions inside. The damping matrix in the acoustic formulation is given by the absorbing boundary conditions. So this is the only damping we have modeled. So it also only comes from the boundary elements in this of low rank, so to say. It doesn't contain elements in the complete system matrix, but only for the boundary degrees of freedom. And the stiffness matrix is again computed by the gradient operators of the ansatz functions. On the right hand side, we have a forcing vector that comes from the inhomogeneous Dirichlet condition, Neumann conditions, and the system is of standard second order type. So we have an ordinary differential equation system in time, which we can solve in the time domain, for example, by forward integration of time. So this brings us to the analysis types. We have three analysis types we can do. We can do the harmonic analysis to compute steady state response to harmonic forcing. We can do eigenvalue analysis to compute the acoustic natural modes and the corresponding natural frequencies. And we can do transient analysis by forward integration in time to compute the transient response. Since acoustics is a dynamic phenomenon, a static analysis doesn't make sense here. How do we have now to discretize acoustic simulations? So now we are already in the tips of modeling acoustics. First, note that the wave equation has smooth solutions. So higher order elements, for example, quadratic ansatz functions, are beneficial in this case. You should also try to avoid mesh distortions, since acoustics is a little bit more sensitive to that than, for example, mechanics. You should always consider the frequency content of the excitation signal, since it determines first the wavelength and also the period, the oscillation period of the changes in the solution. So you should use 10 to 20 linear elements per wavelength. This gives you the spatial resolution. And you should use, if you do transient analysis, 10 to 20 time steps per period. So what you can see is that the required spatial discretization is frequency dependent. The highest frequency you want to investigate leads to the smallest wavelength and therefore determines the mesh size you need to use to resolve the spatial phenomena in the acoustic formulation. And similarly, the frequency of the excitation signal, in case it's transient, will give you the required time step for a transient simulation. What output results do you get in acoustic simulations? They depend on the formulation. Be careful. If we have the pressure formulation, we have a primary result of the acoustic pressure, which is defined on the nodes, and the derived result will be the particle velocity. And in the case of the potential formulation, our primary result is the acoustic scalar potential defined on the nodes, and the derived result will be the acoustic particle velocity or the pressure. Both are obtained from applying differential operators on the acoustic potential. We have a few more acoustic quantities we can output. We have the so-called acoustic intensity, which is defined as acoustic pressure times particle velocity. We can use, again, the decibel scale on the intensity to, and what usually is done here to get this scale is, again, we average over some time period capital T in order to get an average value of the typical dynamically varying intensity value. We have also the acoustic power, which is simply the intensity integrated over an area gamma, again with a decibel value, and again with the time averaging. So this should be actually a time average in the PA here. Note that the reference value are defined via the threshold of hearing. So this is where the reference values for IA and PA come from. And the final acoustic quantity is the acoustic impedance, which is defined as the ratio of pressure over velocity in direction. So note that the acoustic